In this video, I will work out various examples of how to use the substitution rule to compute antiderivatives. These are just computational examples. If instead you're interested in the theory behind the substitution rule, why the method works, I invite you to watch the previous video instead, which is linked in the description. These are the examples I will work with, roughly in increasing order of difficulty. They're all well suited for substitution. I invite you to pause the video, try to compute this antiderivative first, and once you are ready, keep watching for the solution. For my first example, I want to calculate the antiderivatives of x squared sine of x cubed plus 7 with respect to x. The difficulty in this case is the argument of sine is x cubed plus 7, that makes it complicated. But conveniently, the derivative of x cubed plus 7 is basically x squared, up to a multiplying constant. This suggests trying the substitution u equals x cubed plus 7. If I do this, I also need to change the differential, and then the u will be the derivative of x cubed plus 7, which is 3x squared times the x. And I already see why this was a good idea, because the term I need for the differential is right here in the integral. Let me rearrange the function a little bit. I need 3x squared dx for the differential. I had to multiply by 3, so I also divide by 3. And there, now this is ready for the substitution. I get 1/3 of sine of u du. Now, if I compare the original integral with the new one is definitely simpler. This is an indication that this was a good idea. The substitution has been helpful. And in fact, I know that an antiderivative of sine of u is simply minus cosine of u. Finally, now that the integration is over, I can undo the substitution. I get minus 1/3 of cosine of x cubed plus 7, plus an integration constant, and that is the final answer. And of course, we can verify this final answer. We can take the derivative and check that it is the function I started with. For my second example, I want to integrate tangent of x with respect to x. It's not apparent at first sight that a substitution may help here. So before I do anything, I'll use the definition of tangent to write it as sine over cosine. And now let's look at the function in this form. The numerator, sine, is the derivative of the denominator, cosine, times minus 1, but that doesn't matter. This suggests that I could do a substitution. U equals cosine of x. Why? Because the derivative is already there at the top. Let's try that. I will try the substitution u equals cosine of x. If I do that, I also need to change the differential. And then du will be the derivative of cosine of x, that's minus sine x, times the x. And as I said earlier, the reason this is a good idea is because the piece I need for the differential is already there at the top. Perfect. This is ready for substitution, so let's do it. I get the integral of minus du over u. And I know an antiderivative of 1 over u. I get minus logarithm of absolute value of u plus an integration constant. And now that the integration is over, I can undo the substitution, and I get minus logarithm of the absolute value of cosine of x plus c. And this is the final answer. Like before, I can verify this answer. I just need to compute the derivative of this function explicitly and see that it is equal to tangent of x. For my last example, I will integrate x cubed times the square root of x squared plus 1 with respect to x. The part that makes this difficult is the square root. I am tempted to try a substitution, u equals the thing inside the square root, to see if it simplifies this. However, this problem is not as straightforward as the previous two. what I have outside of the square root is not simply the derivative of what I have inside the square root. Nevertheless, I'm going to try. I will try the substitution u equals x squared plus 1. Why? Well, I don't know if this is going to work, but it's worth a try, because if it works, transforming the thing inside the square root into the variable is bound to simplify the expression and make this integral easier. So let's see if it works. If it doesn't, I will try something else. Now, if I want to try this, I also need to change the differential. And then du will be the derivative of x squared plus 1, that is 2x times dx. So I need 2x for the differential. I have x cubed. I can separate that as x squared times x. And then I can multiply and divide by 2. Great. I have the piece I need for the differential. Now, can I execute the substitution? I need to transform everything else in terms of u. X squared plus 1 is u. But what about this other x squared? Well, I can rewrite x squared as u minus 1. This seems to work. Let's do it. I get 1/2 of the integral of u minus 1 times root u with respect to u. And now let's pause for a moment. The transformed integral is definitely simpler than the original integral. So this is progress. Doing a substitution was a good idea. It helps. I'm not done yet, but this has helped. Now, the best way to complete this integral is probably to multiply it out. I get 1/2 of the integral of u to the 3/2 minus u to the 1/2 du. And now I think I know how to compute these antiderivatives. It is 1/2 of u to the 5/2 over 5/2 minus 1/2 of u to the 3/2 over 3/2 plus an integration constant. Excellent. And now that the integration is done, I can undo the substitution, and I get 1/5 of x squared plus 1 to the 5/2 minus 1/3 of x squared plus 1 to the 3/2 plus the integration constant, where I have also simplified the coefficients. And this is the final answer. I could also simplify this final answer a little bit by factoring root of x squared plus 1, but I'm not going to bother. Like in the previous two examples, I can verify that this answer is correct by taking this expression, computing the derivative, and verifying I get back what I started with. Out of all the examples, I like this one the most. With the first two examples, I could probably have gotten away with just using guess and check. But for this one, I don't think guess and check by itself could have been enough. This example illustrates the full power of the substitution rule.